Math Model, Semester 2, Section 251 on symmetry. Okay, so it says for number 1, summarizing in your own words, define symmetry. So what I put was, it's the ability for a polygon, a shape, or an insect to be the exact same on both sides. In my opinion, that's what symmetry is. But this says the property of having a line or axis that a given shape that splits a given shape into two identical parts. And of course, you can't have more than one line of symmetry. So I'm gonna write that down. That's my what a book's or apex definition of symmetry: the property of having a line or axis that a given shape splits into identical parts, and you can't have more than one. When I said earlier an insect, I was really thinking about a butterfly, because normally when you see butterflies, their wings are exactly the same on the left and the right side. So that was my thought behind it. Okay, number 2 says organizing information. There are 2 types of symmetry that we're going to focus on in this lesson: reflectional symmetry and rotational symmetry. So reflectional symmetry is, by definition, the quality a design has if it looks the same when it is reflected around a line or an axis in its plane. Okay, the test for reflectional symmetry is if a line of symmetry can be drawn where it's exactly the same on both sides. So for example, you can look at the letter A there. This letter A has only one line of symmetry, and that's the line that's going straight up and down, split in half. Oops, that was too much. So let me put that back. Okay, but yeah, it's just this line right here that's going down the middle of the letter A that makes both sides the exact same. The other type of symmetry we're going to focus on is rotational symmetry. And remember, rotation just means to spin. So it's the quality a design has if it looks the same when it's rotated around a point in the plane. The test for rotation is if there is a point of symmetry. And when you think of a point of symmetry, think of like on a twister board, the game where you spin it around, and the little thing to tell people right hand red or left hand blue or right foot whatever, that's a point of symmetry, the very center of where you spin it. So this letter S here is kind of like a bolded letter S, and so it has rotational symmetry. If you were to spin it around, it should look the same upside down. And if you don't believe me, just take your paper, write an S, and spin it around. If you make it as plainly shaped, not like a fancy S like this or anything, because of course this little curl right here is gonna mess you up. All right. Okay, and so it says number 3, making mental images. What are 2 ways to find a shape's line of symmetry? The first thing you can do is look for a line that divides the shape into equal parts, or congruent, whichever word works best for you. I like equal. It's short and sweet. Boom, boom, equal sign. All right, number 2, you want to imagine folding a shape in half so that the 2 halves are equal. Okay, so number 4 says draw all lines of symmetry for each regular polygon below. Now, when you see lines of symmetry here, we're going to draw a line that can split it into equal parts. But what you got to know about a regular polygon is that the angles are equal and also the sides are equal. That's what makes it regular. All the sides are equal. So in an equilateral triangle, you can draw the following lines of symmetry. Okay, so I just tried to draw some perfect lines of symmetry and it didn't work. So I'm going to just freehand draw them. Hope you don't mind. So here's one right there through the triangle. I can fold those 2 halves and they will be equal. But here's one you may not have seen. It goes right here, right through there. Okay, or there's another one which is right here. So an equilateral triangle happens to have 3 sides. Well, all triangles have 3 sides, and we have 3 lines of symmetry. A square, I'm just going to freehand them. Oh gosh, that was bad. Okay, so right here through the middle. Okay, right there, that's 2, and then 3 and 4. Okay, and the way how The way how you can tell how many lines you have, if you lose track of count, what I do is this. I do 1, 2, 3, whoops, okay. I think, okay, and 4. All right, and that way I know I have 4 lines of symmetry going right there. Okay, so then you have a regular pentagon. Oh wait, a square, it has 4 sides, and you have 4 lines of symmetry. So a regular pentagon, it has 5 sides. How many lines of symmetry should it have? You guessed it, it got 5. Okay, so here we go. I want to start a different point. So there's one line right there. Okay, and we have another line here, and we have one there, and we have one there, and one, whoops, that one was really bad. There's one more. Okay, I need to go through this point. Okay, there. 1, 2, 3, 4, 5. Yep, that's it. So here we go. 1, 2, 3, 4, 5. So we have 5 lines of symmetry there. Let's keep going. Okay, so I kind of gave this one a weight. It says, what's the relationship between the number of lines of symmetry in a regular polygon and the number of sides it has? So the relationship between the lines of symmetry and the number of sides is that it's equal. I'm going to just take the shortcut. The number of lines of symmetry a polygon has is equal to the number of sides. And I would just say it's equal. Okay, so the symmetry rule. If a regular polygon has n sides, then it has n lines of symmetry. Hold on a second. Okay, so all that means is that n could be any number. It's a variable. So it could be a 3-sided triangle with 3 lines of symmetry. It could be a 4-sided square with 4 lines of symmetry. A pentagon, 5 lines of symmetry. Hexagon, 6 lines of symmetry. And it keeps going. Heptagon is 7 lines of symmetry. You get the point. Okay, let's keep going. Number 7. Number 7 says rotational symmetry. And I wrote a note on here, and if you give it a try, okay, page 14 through 16 really does a great job at showing you this picture that you can manipulate and see what it means by the rotational symmetry about a point. Okay, because this chart is very dry, so I thought it might help a little bit. So what you're going to see is that in rotational symmetry, there's the types. There's 2-fold, 3-fold, 4-fold, and 5-fold. Where am I getting those numbers from? Right here. 2-fold, 3-fold, 4-fold, 5-fold. Can't say that fast. And the meaning of those, and then how all the points move. So in a 2-fold, there are only 2 different places where the design can be rotated and still look the same. Only 2. All right. How are all the points going to move? The points will move in groups of 2 around the center point of symmetry. And what you're going to see is that 3-fold, there are only 3 different places where the design can be rotated and still look the same in groups of 3 around the center point of symmetry. So what you can see here is that pretty much everything repeats itself. So I'm gonna just fill it in. Hold on. And if you can't understand my handwriting, it's okay. It says 2, 3, 4, and 5 over here, and then 2, 3, 4, and 5 over there, and then the second word is point on this side. Second word is point, and over here the second word is rotated. Okay, but like I said, this chart is very boring. So look at, there's something that's important on page 14, and I want you to see that. Okay, go there. Okay, and number 8 says making mental pictures. How is symmetry in the real world different from symmetry in geometry? Well, what it says is that symmetry in the real world is called a loose symmetry. Let me write it down. Hold on one second. I didn't realize until now I was writing with the green on yellow, and so it probably wasn't easy to see. I'm sorry about that. But what it said was real world symmetry is loose symmetry, and geometric symmetry is precise. And whoops. Okay. And this right here, there's an example on page 17. Whoops, 17 inside of Apex. So real world symmetry, the best way to describe it is, say, like the butterfly. Okay, both of the wings are supposed to be exactly the same. Could they be different? Yeah, that's how come, like, identical twins always have like something a little bit different about them. Okay. So geometric symmetry is like, it's precise. There's tools involved in this, and there's compasses and protractors and rulers, and everything has to move at the exact same pace at the exact same time, and it must be identical. Okay. So that's that for right now. But making mental images number 9 says list 3 things in the real world that seem to have symmetry. And I like that they say seem to have symmetry. Tell if that symmetry seems to be reflectional, rotational, or both. And hint, look at objects in the room around you. So what I looked at, I had a fleur-de-lis, the saint symbol, on my desk. So if you come look at my desk, I got it. It's my cup thingy. The thing that I sit my cup on. I can't think of the name of it right now. Jeez, that's bad. Okay, but here's one. And I'm gonna just freehand write these. I hope it doesn't look too bad. But the butterfly would have reflectional symmetry, where the wings are the same on the left and the right. A stop sign. A stop sign, I believe, is an octagon. So that would have reflectional and rotational symmetry. So I'm gonna just put both for the stop sign. And I had another one written down. A cylinder, like the cylinder that I keep the pencils in. A cylinder, like a coffee canister. That has both. And like an airplane. If you look at like the cartoon type airplane that you draw, that looks awful, but that's okay, because it's my picture. Well, I don't want to put a line right there, so let me take that away. But well, if you have windows on this side, you gotta have windows on the other side, right? And at the front, like, it's all the way around so the pilot can see. So that's kind of like reflectional symmetry, because it's the same on the left side of the plane and on the right side. Okay. Oh, Tazelle gave me this one, the circle with a line through it, like a no smoking sign, a do not enter sign, or something like that. You can spin this around and it should be the same. And yeah, but I want to give an example of what's not perfect symmetry, and sometimes it may surprise you, but copies on a copy machine. As a teacher, we make like a lot of copies, and so those copies, sometimes if you have things with lines and angles, a lot of times when I would teach that lesson and I wanted the students to measure it with a protractor, it would not copy. Every single time we got different angle measures because the copier is just a little bit off, and it may just be off by boop, that much. I don't know if you saw that dot. I'm gonna do another one in a circle. Boop. Might be off by just that much, but just that little bit will change it totally. So I'm sorry, I feel like I'm rambling, but anyway, I wish you all the best with your lesson. All right, you know Miss Gable loves you very much. If you get a chance, do the checkup practice problems, and if you have a question, of course, just let me know. Thank you and have a great day.